Before the engine noise, before steel replaced hands, there was silence in the vegetable rows. A silence broken only by hose, boots, and breath. In the late 1940s, American agriculture was already mechanized in appearance, but not in every corner of the field. Large grain farms had tractors, combines, and systems built for scale. Small vegetable farms did not, and that gap defined a problem few manufacturers were willing to solve. Market gardens, truck farms, and diversified vegetable operations relied on labor-intensive work. Crops were planted in tight rows. Soil had to be cultivated frequently to control weeds. Timing mattered because vegetables compete poorly when weeds get ahead. The work was repetitive, slow, and physically exhausting. One person with a hoe could manage only a limited area per day, and hiring seasonal labor was expensive, uncertain, and increasingly difficult after World War II. Farmers knew tractors existed, but most tractors were designed for open fields, not precision. They were wide, tall, and heavy. Their engines sat high, their hoods blocked visibility, and their wheels crushed crops when turning. Even so-called small tractors were built to pull plows, discs, and wagons, not to work inches away from fragile plants. Using them in vegetable rows was risky and often destructive. The result was a strange contradiction. Agriculture was modernizing rapidly, yet many farmers were trapped in pre-mechanical routines. A single acre of vegetables could require dozens of hours of hand labor every season. Weed pressure could ruin yields. Miss a cultivation window by a few days, and the field could be lost. This was not inefficiency at the margins. It was a structural bottleneck in food production. The problem was not lack of technology, but mismatch. The machines that existed solved problems of acreage and power. They did not solve problems of access, visibility, and control. Vegetable growers needed something different. A machine light enough not to compact soil, narrow enough to fit between rows, slow enough to work carefully, and cheap enough to justify on small acreage. Most manufacturers ignored this need. The market seemed too small, too fragmented, too specialized. But the problem remained, season after season, field after field. It waited quietly between the rows, in the space where hands were still doing the work of machines that did not yet exist. It was here, in this overlooked scale of farming, that efficiency was measured not in horsepower, but in human endurance. Every improvement mattered, even small ones. The unresolved tension between growing demand for vegetables and the limits of manual labor set the stage for an unusual response, one that would challenge assumptions about what a tractor should look like and who it was really built for. Next chapter. By the standards of the late 1940s, tractors were already considered mature technology. Manufacturers focused on reliability, power, and versatility. For grain, hay, and livestock farms, this made sense. Fields were large, rows were wide, and the goal was to cover as much ground as possible with each pass. But the very features that made tractors successful in those environments made them unsuitable elsewhere. Standard tractors were built around pulling power. Their weight provided traction. Their size allowed stability. Their engines were mounted high and forward, covered by long hoods designed to protect components and signal strength. For vegetable farmers, these same traits became liabilities. Heavy machines compacted soil, reducing root growth and water infiltration. Wide wheel spacing limited how close a tractor could operate to crops. Turning at the end of a row often meant crushing plants or wasting valuable growing space. Visibility was another critical issue. Cultivating vegetables requires precision measured in inches. Operators need to see the soil, the crop, and the implement at all times. Traditional tractor layouts place the driver behind the engine and hood, far from the working area. Even experienced operators struggled to judge spacing accurately. A moment of misalignment could damage an entire row. Cost further complicated adoption. A tractor represented a major investment. For a farm of only a few acres, the economics rarely worked. Fuel consumption, maintenance, and storage added ongoing expenses. Many vegetable growers calculated that hiring labor, even at rising wages, was still safer than risking a machine that might not actually reduce work. Attempts to adapt existing tractors often failed. Narrow front ends improved turning radius but reduced stability. Smaller models still share the same basic layout and limitations. Aftermarket cultivating attachments helped, but they did not solve the core problem of control and visibility. The industry treated these shortcomings as edge cases. Vegetable farming was seen as specialized, not central. As long as large-scale row crop agriculture drove sales, design priorities remained unchanged. The assumption was clear. Farmers would adapt to the machine, not the other way around. But adaptation has limits. By the late 1940s, vegetable growers were reaching them. Labor shortages, rising demand, and tighter margins made the existing system unsustainable. What they needed was not a smaller version of the same tractor, but a fundamentally different approach. One that started with a task, not a tradition. The shift did not begin in the field. It began on paper, inside the engineering culture of Allis-Chalmers, a company best known at the time for large tractors, industrial machinery, and power equipment. In the late 1940s, Allis-Chalmers already had a broad product line, but it also had something less visible: internal discussions about specialization. Engineers were increasingly aware that not all farms scaled in the same direction. Vegetable farming presented a unique contradiction. It demanded mechanical assistance, but rejected mechanical bulk. Engineers studying the problem noticed that the limiting factor was not power. Cultivation tools required relatively little force. What mattered was control, accuracy, and visibility. If a machine could move slowly and precisely, it did not need to be large. This realization inverted the usual design logic. Instead of starting with the engine and building a tractor around it, the design began with the operator's line of sight. Engineers asked a simple question: what if the driver could see the soil directly beneath the machine? What if the crops were never hidden by a hood or engine block? From that question came a radical layout. The engine would be placed behind the operator, not in front. The front of the machine would be open. Implements would be mounted centrally, between the wheels, where they could be seen clearly during operation. This was not an aesthetic choice. It was a functional one, driven entirely by the task of cultivating narrow vegetable rows. The result was the Allis-Chalmers Model G, introduced in 1948. It was powered by a small gasoline engine, producing modest horsepower, roughly within the typical range for garden-scale machinery of the era. But horsepower was never the point. The Model G was light, low to the ground, and narrow. Its frame was minimal. Every unnecessary component was removed. From a manufacturing perspective, the idea was risky. The machine did not resemble other tractors. It did not promise versatility across all farm tasks. It was intentionally limited, built to do a few jobs well rather than many jobs adequately. That ran counter to the prevailing market logic. But for the engineers involved, the logic was clear. This was not a compromise machine. It was a purpose-built answer to a specific, persistent problem. And in that clarity, the Model G quietly crossed a line, away from tradition, and towards something that looked wrong, but worked differently. The first reaction to the Model G was not admiration, it was confusion. Even experienced farmers, used to decades of evolving tractor design, struggled to interpret what they were seeing. The machine looked incomplete, almost inverted. Where other tractors projected strength through size and mass, this one emphasized openness and visibility. It broke visual expectations before it ever broke ground. The most striking feature was the layout. With the engine placed behind the operator, the front of the machine felt unusually exposed. There was no long hood stretching forward, no protective shell enclosing the power unit. Instead, the operator sat closer to the action, looking directly at the ground between the front wheels. For some, this seemed unsafe or impractical. For others, it simply looked wrong. This perception mattered. Agricultural equipment is not judged only by performance, but by trust. Farmers invest in machines they understand at a glance. A tractor is both a tool and a signal of reliability. The Model G disrupted that signal. It did not visually communicate power in the traditional sense, even though it was engineered to do its job effectively. The narrow stance reinforced this impression. Designed specifically to fit between vegetable rows, the machine's proportions were unlike standard row crop tractors of the era. It appeared almost delicate, especially when compared to heavier general-purpose machines. Yet this thinness was intentional. It reduced crop damage and allowed precise movement through tightly spaced plants. Another unusual aspect was the central mounting of implements. Instead of pulling tools behind the tractor, many attachments were placed beneath or between the wheels. This allowed the operator to watch the cultivation process directly. From an engineering standpoint, this improved accuracy. From a cultural standpoint, it challenged the idea that tractors should work in front of the operator's attention rather than under it. Even the controls contributed to the sense of unfamiliarity. The driving position prioritized function over tradition. Visibility replaced enclosure. The machine did not try to hide its mechanics. It exposed them, as if inviting the operator to understand every movement of soil and steel. At demonstrations and early showings, reactions were mixed. Some observers immediately recognized the advantage: precise cultivation in tight rows without crop damage. Others focused on what it lacked: size, weight, and the visual reassurance of conventional tractor design. The Model G did not fit existing mental categories. But confusion is often the first stage of adaptation. Beneath the skepticism, a quieter recognition began to form among vegetable growers. This machine was not trying to be everything. It was trying to solve one specific persistent problem. And in doing so, it forced people to reconsider what a tractor could look like when function, not tradition, defined its shape. To understand why the Model G worked differently, you have to ignore horsepower for a moment and look at geometry. The engineering philosophy behind the machine was built around spatial precision, not raw pulling force. In vegetable farming, the limiting factor is not how much soil a tractor can move, but how accurately it can move between living plants without disturbing them. The power unit in the Allis-Chalmers Model G was a small gasoline engine typical of compact agricultural tractors of the late 1940s. It was not designed for heavy draft work like deep plowing or large-scale tillage. Instead, it provided enough torque for low-speed cultivation tasks, where control mattered more than speed. The relatively low power output also reduced weight requirements, allowing the entire machine to stay light and less destructive to soil structure. The most important mechanical decision was the mid-mounted implement system. By placing cultivation tools between the front and rear wheels, engineers effectively aligned the working zone with the operator's direct line of sight. This reduced error margins dramatically. Instead of estimating position from behind the hood, the operator could see the exact interaction between steel blades and soil in real time. Weight distribution was another key factor. With the engine located at the rear, the machine achieved a balanced center of gravity. This was not about speed or traction in the traditional sense. It was about stability during slow, precise movements. A stable platform meant the implements could maintain consistent depth, which is critical when working near shallow-rooted vegetable crops. The narrow frame was not simply a size reduction. It was a functional constraint derived from crop spacing. Vegetable rows often measure only a few tenths of centimeters apart. Any deviation risks crop damage. By designing the tractor around these constraints, engineers effectively reversed the usual process. Instead of adapting crops to machinery, they adapted machinery to crops. Steering geometry also reflected this philosophy. Tight turning capability allowed the machine to navigate raw ends without excessive overlap or destruction of planted areas. In large tractors, turning radius is often a secondary concern. In the Model G, it became a core design parameter. However, this specialization came with clear limitations. The machine could not replace general-purpose tractors. It lacked the power and structural robustness required for heavy fieldwork. Its value existed only within a specific agricultural context. But within that context, the design was almost surgical. Every mechanical choice reinforced a single idea: reduce uncertainty between operator, machine, and plant. In doing so, the Model G turned a simple engineering principle into a quiet transformation of how precision farming could be achieved. The first time the Model G left the dealership floor and entered real farmland, expectations were cautious rather than enthusiastic. Early buyers were not large industrial operations, but small vegetable growers who had been struggling with labor shortages and inconsistent yields. For them, the machine was not a novelty, it was a calculated risk. On the first fields, the difference was immediate but subtle. Operators did not report raw power or speed. Instead, they talked about something less obvious: control. For the first time, they could see the soil being worked directly beneath them while maintaining alignment with the crop rows. That visibility changed the rhythm of cultivation. Movements became slower but more deliberate. Farmers who had spent years relying on hand labor or adapted general-purpose tractors noticed a reduction in accidental crop damage. In vegetable production, even small losses along row edges accumulate into significant yield reductions over a season. The Model G did not eliminate mistakes, but it reduced their frequency by making precision easier to maintain. Reactions varied depending on prior experience. Operators transitioning from hand tools described the machine as a major relief in physical workload. Those who had used standard row crop tractors were more critical at first, noting its limited versatility. It could not replace a general tractor, and it did not pretend to. Its narrow focus required a shift in mindset as much as in equipment. Field conditions revealed both strengths and weaknesses. In soft soil, the lightweight structure helped prevent excessive compaction, preserving root structure in sensitive crops. In uneven terrain, however, the low mass required careful handling to maintain stability. It was not a machine for speed, it was a machine for patience. Maintenance feedback was also notable. Simpler construction meant fewer components under stress, but its specialized layout meant that adjustments and repairs required familiarity. Dealers and mechanics had to learn a new configuration that differed significantly from conventional tractor designs of the era. Despite these limitations, early adopters began to extend usage beyond initial expectations. What started as cultivation between rows gradually expanded into related tasks like weeding, shallow tillage, and light field preparation. Each use reinforced the same conclusion. The machine was not broad in capability, but highly efficient within its narrow domain. By the end of its early field trials, the Model G had not transformed agriculture overnight. Instead, it had proven something more specific. It demonstrated that precision farming tools did not need to compete with large tractors on power. They only needed to outperform them in the narrow space between crops. And in that space, the logic of design began to feel less experimental and more inevitable. Real-world operation of the Model G revealed something that engineers had suspected but could not fully verify on paper. Vegetable farming is less about peak performance and more about repetition under constraint. Day after day, the machine worked not in open fields, but in narrow corridors of living crops where every inch mattered. In wet conditions, the lightweight structure of the Allis-Chalmers Model G became an advantage. Unlike heavier tractors, it was less likely to sink deeply into softened soil, which helped preserve the structure of planting beds. Farmers working after rainfall noted that the machine could return to fields sooner than expected, reducing delays in cultivation schedules that often determine crop health in fast-growing vegetables. However, those same wet conditions also exposed its limits. Traction was not infinite, and careful throttle control was necessary to avoid slipping, especially when implements were engaged in soil. Operators learned quickly that the machine demanded attentiveness. It was not forgiving of careless driving, but it rewarded precision with consistency. In dry seasons, dust and visibility became the dominant challenge. Ironically, the very advantage of close visual control over the working zone also meant that dust from cultivation could interfere directly with the operator's line of sight. Farmers developed informal techniques to manage this, adjusting speed and timing passes to match wind conditions and soil moisture. Across different regions, the Model G found its most effective use in intensive vegetable systems. Onions, lettuce, carrots, and similar crops, where row spacing remained tight and frequent cultivation was necessary. In these environments, the machine was not competing with large tractors. It was replacing repetitive manual labor that had previously defined the scale of production. Some farms integrated it into a broader system. Hand labor was still used for delicate tasks like thinning and harvesting, but mechanical cultivation reduced the time spent on weeding and soil aeration. This hybrid approach increased overall efficiency without fully eliminating human labor. There were also operational realities that limited its spread. Transport between fields required planning because the machine was not designed for long-distance road travel like larger tractors. Storage and maintenance spaces needed to accommodate its unusual frame geometry, which did not always fit existing sheds designed for conventional equipment. Despite these constraints, long-term users began to view the Model G less as a machine and more as a specialized tool integrated into the rhythm of seasonal work. It did not redefine farming in a dramatic way. Instead, it changed the tempo of specific tasks, making them more predictable and less physically exhausting. Over time, this quiet reliability became its defining characteristic. It was not the strongest or fastest machine in the field, but in the narrow spaces where vegetables grew and weeds competed for survival, it became a steady presence that reshaped how precision fieldwork was understood. The Model G never became a universal tractor. Its spread followed a different pattern, shaped less by mass demand and more by specific agricultural niches that already understood its purpose. Vegetable producers, experimental farms, and a number of small diversified operations formed its primary user base. Unlike general-purpose tractors that define mid-century agricultural expansion, this machine did not scale outward into all farming categories. Instead, it concentrated inward, becoming more valuable where crop spacing was tight and labor costs were high. In those environments, its design philosophy aligned directly with daily operational needs. Dealers noted that adoption was steady rather than explosive. There was no dramatic surge in sales, but a consistent flow of interest from farms that had already experienced the limits of hand cultivation. Word of mouth played a larger role than advertising. Farmers trusted field results more than specifications. At the same time, the broader agricultural machinery industry was beginning to recognize a structural shift. The post-war period was not only about bigger tractors and higher horsepower. It was also about specialization. The success of machines like the Model G demonstrated that efficiency gains could come from narrowing focus rather than expanding capability. Some manufacturers observed and responded indirectly. Instead of copying the exact layout, they began exploring dedicated cultivation tractors, inter-row equipment, and modular tool systems. The idea that a tractor could be designed around a single crop system rather than all crops slowly entered engineering discussions. However, the Model G remained visually and conceptually distinct. Its rear engine layout and open front design were not widely replicated in identical form. The risk of departing too far from conventional tractor aesthetics limited broader imitation, even when the functional logic was understood. Over time, this created a split in the market. One direction emphasized power, versatility, and scale. The other emphasized precision, narrow use cases, and close interaction between operator and crop. The Model G became part of the second category, not as a dominant force, but as a reference point. By the end of its production life, it was clear that its influence was not measured in volume. It was measured in ideas that began to spread quietly through engineering culture, reshaping how designers thought about the relationship between machinery and specific agricultural tasks. Long after the Model G left active production lines, its impact continued to echo in ways that were not immediately visible in sales charts or factory output. In the broader agricultural economy, the post-war mechanization boom is often remembered through large tractors and high-capacity harvesters. But beneath that dominant narrative, a quieter transformation was taking place in specialized farming systems. Vegetable production in particular began to evolve into a more structured and efficiency-driven sector. The presence of machines like the Allis-Chalmers Model G had normalized the idea that not all mechanization had to be large-scale. Precision could be its own form of productivity. That shift influenced how farms calculated labor requirements, planting density, and cultivation schedules. Economically, this mattered because vegetables occupy a different risk profile compared to grain crops.
Losses in row crops are often incremental. In vegetables, they can be sudden and severe. A missed cultivation window or uncontrolled weed growth can reduce yields dramatically within a short time. Machines that improved timing and consistency, therefore, had an outsized economic effect, even if their horsepower was modest. At the same time, the labor structure of farming continued to change. Seasonal workers were still essential, but their role gradually shifted from repetitive cultivation tasks toward more selective, higher-skill activities such as harvesting and crop management. Machines took over the physically exhausting, repetitive soil work, while humans remained critical for judgment-based tasks. This division of labor was not always smooth. Some farms struggled to justify the investment in specialized equipment for relatively small acreage. Others found that the machine required a new mindset, where efficiency was measured not by speed across fields, but by accuracy within rows. The transition was gradual and uneven, depending on region and crop type. Technically, the Model G also contributed to a broader engineering awareness that operator visibility and task-specific design could be as important as mechanical strength. This idea would later appear in different forms across agricultural equipment design, even when the exact configuration of a Model G was no longer used. By the late 20th century, many of these machines had been replaced or retired. However, their influence persisted in design principles embedded in newer equipment. The concept of tailoring machinery to crop geometry rather than generic fieldwork became part of standard engineering thinking, even if rarely attributed directly. In this sense, the Model G's legacy was not tied to its production numbers or market dominance. It lived on in the subtle recalibration of priorities within agricultural engineering, where precision systems began to sit alongside power systems as equally important tools in feeding a growing population. At the edge of a vegetable field at sunrise, the air still carries the memory of machines that once reshaped how every row was cultivated. The Model G no longer stands there in many places, but its design logic remains embedded in the way modern precision farming systems approach narrow row crops. In the decades after its introduction, farms that once relied on hand labor for cultivation gradually shifted toward mechanized inter-row systems that prioritized visibility and control over brute force. This transition did not happen evenly, and in many regions, small vegetable producers continued to rely on mixed methods, balancing human labor with specialized machines. But the principle introduced by machines like the Allis-Chalmers Model G had already taken root. Farming efficiency
could be achieved through precision rather than scale alone. Returning to a single field today, the contrast is subtle but important, as modern equipment moves through rows with systems that trace their conceptual origin back to early specialized tractors. The operator still sits above the crop, still watches the soil closely, but now assisted by sensors, hydraulics, and control systems that extend the same idea of precision. In that continuity, the Model G is not remembered as a powerful machine, but as a quiet step toward designing tractors around the spaces between plants. And in a small sense, every carefully guided pass through a vegetable row today still echoes the decision to prioritize sight, control, and narrow purpose over universal strength. At the edge of those fields, where soil is turned with quiet accuracy, the absence of the old machine is almost as telling as its presence once was.
And so the story returns to where it began, not with noise or scale, but with the narrow space between crops, where a different kind of tractor quietly changed what farming could be. Even today, engineers studying agricultural robotics often rediscover the same constraints that defined its original design. The challenge remains unchanged: how to move through living systems of plants without disturbing what you intend to preserve. And in that sense, the Model G continues to exist not as metal, but as an idea, repeated in every precise pass through a field.